So let's see, if you take a dy dx out, you're left with all this business here. And then of course you just divide by the stuff I don't want. So then dy dx is this. So if I want to know the derivative, the value of the slope at any point on this graph, I have to put the entire point in, because the dy dx is a function of x and y. Yeah, like it. Okay.
That's implicit.
That's implicit. Anytime you start to take a derivative that is not solved for a variable, that's implicit. You haven't explicitly stated what the function is a function of.
Yeah.
Let me ask you this. Is there any reason mathematically that we had to define slope to be the change in y over the change in x? Could we not have defined slope to be the change in x over the change in y? Of course we could. Totally. Everything is made up. I need you to understand. It's based on rules we had to choose. So we made this the x-axis, this y-axis. It could have totally been turned around. It's arbitrary to some degree. Let me see. I need to throw this in here because we haven't talked about this yet. Let me start with a smaller example function or relationship. No, this won't. Yeah, this will work. Okay, there. Okay. Say I want to figure out what dx dy is. How much does x change when I change y? And it actually, to me, it makes more sense with implicitly defined relationships because y is not a function of x and x is not a function of y, not explicitly anyway. So can I change the x value and see what happens to y? That's the traditional way, right? What do we think of slope? If I change the x, if I change the input, what happens to the output? Couldn't I think about it the other way? If I change the output, what happens to the input? That's exactly this question right now. Now, when I do this, everything's dy now. So just go with me for a second. I'm going to show you a shortcut to do this because this is a very hard left turn to take cognitively because we're so used to doing dy dx. But just go with me for a second. This would be 1. This would be e to the x times dx dy. Because now x is assumed to be a function of y. But just go with me for a second. So this was a product rule. I didn't state that, but there's the product rule, yes? Just go with me for a second. Don't write down this if you want to. Then this would be dx dy, y plus x equals 0. I would take this and subtract it to the other side. I'm doing this a little bit quickly because I got a shortcut for you. If I take this out, I would have y e to the x plus y, and then I would divide by that. And then there's my dx dy. Kabam. All right, I love you guys. You're barely hanging on with me. I can feel it. Dude, one thread holding me here, man. Can you guys just take a moment? All right, does everybody really appreciate that? Isn't that awesome? You're like, I barely have dy dx with this implicit shit, and now you're gonna do dx dy to me? That's a really hard ask for a student who's got it already kind of like burned in their brain, dy dx items. Can you guys figure out what dy dx is for this? Let me write it again. This is what I really, really want you guys to focus on right now. If I have this relationship, take a minute and figure out what dy dx is. So this is your standard thing. Figure out what dy dx is. While I double check my work up here, or else everything's going to go to shit. Let's see. That looks good. Yeah, that looks good. Yeah, okay, it should be fine. Yeah. I love you guys so much. You're doing great. So just figure out what dy dx is, right? Like we've been doing. I'm going to kind of start doing, I'm going to start catching up to you a little bit. So there's a product rule, and there's another product rule here. Yes?
Yeah.
So then I'm going to move this guy and this guy over. And here I'm going to get e to the x plus x, and then dy dx is equal to negative y e to the x minus y over e to the x plus x. Now, do you guys notice? Now that's what we've been doing, correct?
Yeah.
And that you kind of got hardwired in your brain a little bit, which is why this is a big ask. Because this involves you going against what's hardwired in your brain, because now you have to realize that when I take a derivative of y, I get 1. And that is a difficult thing to do when you're first learning this. I get that. But does anyone notice something stupid? If I know dy dx, and we can all figure out dy dx, how do I get dx over dy? I just flip the dumb thing. So if there's a problem, don't care what it is, that wants you to figure out dx dy, if I were you, I would figure out dy dx, and then just flip what I get. Do you guys see how those are the same? Those answers are the same, just one is flipped over, yes? They're not the same, I gotta be careful. If I flip this over, don't I get that? If I let the negative go up top. Does everybody see that? Does everybody see that? Hopefully some of us could have, if I let you, you might have thought dy dx, dx dy, those are just flips. It makes sense I just flip the answer, yes? You guys all with me? That's really nice that follows what we would hope would happen. So if there's a problem, and there are problems in the homework that ask for this, I would figure out dy dx and then just flip it. Yes?
So for dx dy, it's literally just the exact same thing, but just y, derivative of y is equal to 1.
Yes, derivative of y is equal to 1. Anything with x in it has to involve a dx dy.
Yeah.
So it's literally the
same,
opposite.
just flip.
And if I were a student taking this class and I started trying to do this, somewhere halfway through the problem I would forget that. And I would start doing dy dx because I'm used to that. But thank God there's just figure out dy dx and then flip it if the problem wants that instead. You're like, I got you. Or try dx dy just to kind of like broaden your brain's hardwire. That works too. Alright, so everybody's semi with me. Semi? What does calculus do for us? If I have a function that's not a line, I can figure out the slope of that function anywhere. What are we now learning calculus can do? The thing that we're looking at does not have to be a function. Is this a function?
No.
This spaghetti thing I'm doing. Does it have a slope everywhere that my finger point is on it?
Yeah.
Yes! So the main thing, the first thing calculus does, there's only two things it does. Calc 1. It figures out the slope, and then it does something else we're going to learn, like the opposite. So it should be independent of if the damn thing's a function or not, because graphically I can see the stupid thing has a slope. Look, right there, it's 0 slope, yes? Ooh, and then it gets big, and then it's infinite, and then it goes over there. I know there's a slope everywhere, and that's the only stupid thing calculus should be able to do. And this is what implicit does for us. It goes, oh yeah, you're right. If I'm on a roller coaster, it kind of goes back on itself. You can still find this derivative. It's not a function, but you can still do this through. Okay. Stop for a minute. I appreciate you guys. Put up with me so long. Okay. So that's implicit. If there's no other specific questions, I'm going to move on.
Explicit.
Huh? This is implicit differentiation.
Yeah, are we going to do explicit?
We've been doing explicit this entire time. So just to really make sure you guys understand, this would be an explicit derivative. That's explicitly defined, yes? Can you see what y as a function of x is exactly? Yes. If I write this, can you solve for y? No?
No. Well, you can, but you would.
Can you solve for y? No, you can't. Because if I try to take a natural log, then these are stuck inside of a natural log. Oh, wait, I need to do that. There we go. It's a little more interesting now. Okay, maybe. The way I had it written was dumb, but it's okay. Okay. We skip section 3.7 and 3.8 just because. One thing I do want to say, before I even get to there, Jeff, you got to finish up inverse trig. Does anyone remember, and this is from section 3.6, so we did this. What was this guy's derivative? Beautiful. And then the one that you're going to forget, understandably, because this guy happens a lot. So it's easy to forget something like this. What's this guy's derivative?
1 over x natural log of b.
Good. Okay. And just remember, by the way, side note, if I have b to the x, what's this guy's derivative?
X to the b.
No.
B to the x natural log.
B to the x, natural log of
b.
b. Now, real quick, what's the relationship between g and h? What's the relationship between the g function and the h function? They're inverses of each other, yes? Do you see what g prime does? It divides by ln b. Do you see what h prime does? It multiplies by ln b, which fundamentally makes sense since they're inherently inverses of each other. The derivatives should be somehow inversely related to each other. Okay, maybe. Okay. So yes, one level is, and again, math is so much a foreign language. What's one level of learning any foreign language? Vocabulary. So what's the level related to that in calculus? Function is derivative. The function is, that's the vocabulary. What about the product rules? Oh, that's grammar. That's the grammar rules of the shit. That's how those derivatives kind of like interact with each other. Yes. Okay. Something else we just barely stepped into. The only inverse trig function that we got its derivative was this guy. Does anyone remember what this guy's derivative was?
One over secant.
At one point it was related to what you're saying, but then we went further.
No.
That is the one inverse trig function I make my students memorize. It is the one that shows up the most often. So if you go to Calc 2, well, hell, if you're in Calc 1, and we are, you're going to see this more than other ones. Calc 2, this definitely shows up more than other ones. Some other teachers might want you to know some of the other inverse trig. Oh well, if you get to them, then learn them. For me, this is the one that makes the most sense to memorize. So let's prove some of the other ones. Let's figure out what some of the other ones are. We proved this the exact same way we proved this. The method we used was the same. So let me start us off with, what about, let's just go back to basics. What about arc sine or inverse sine? Let me write this even better. How the shit do you want to bring in limit definition of the derivative? Let me just go through all the steps here. Dear God, no. You guys remember when we first did like the derivative of tangent? What did we have? I don't know if you guys remember. What did we have to know to be able to do tangent's derivative? We had to know quotient rule because tangent is sine x over cosine x. Yes. So we learned quotient rule, and then we went, oh shit, we can do tangent now. We did it. We learned implicit differentiation, and then we go, oh shit, now we can do this natural log, and we can do this inverse. Because how can I rewrite that dumb thing in terms of something I know the derivative of? Yes?
X cosine y.
Yeah. Do you guys like him much compared to other things? Do you like inverse trig? So if I just take the sine of both sides, they'll die, yes? So then I get x equals sine y. Can you take this guy's derivative now? What method do you have to use to take that guy's derivative? Understanding that unless otherwise stated, I want dy dx.
Chain rule?
Chain rule. Or more generally, I also have to use implicit differentiation. Go ahead, do it. I'll wait. Do it. Do it. I've never done that. I'm curious about that. Let me see. I've never done something else here. Let's see if this works. Oh, this is neat. This would work. I'll show you this after you guys do it the hard way. Such a nice guy. Yeah, this totally would work. Holy shit. I never thought about that. That's what I love about math, man. I know a decent amount of math, but every damn time I teach this, I notice something new. Alright, so what's the derivative of x? That's insane. What's the derivative of sine stuff? Cosine stuff times dy dx. Yeah. So then dy dx equals yeah, 1 over cosine y. How do I figure out what cosine y is? Because real quick, just to make sure you understand. My original function was a function of what? What's my original function a function of? X. So I need my derivative to be a function of x. Currently it's a function of, oh shit. Does anyone remember how to figure out what cosine y is? Do I know what sine y is?
Yeah.
Yeah, so there's two ways you can do this. You can do the representative triangle way, which is kind of like the way I default. Or, yes, we've done representative triangles before, yes. The angle would be y, it would be x over 1, you know what sine is with the ratio, you know where to put x, where, all that kind of shit, yes. Or, you could just use an identity. Are sine y and cosine y related to each other somehow? They are, totally. What's sine squared y plus cosine squared y? 1. Could you solve that for cosine y since we know what the hell sine y is? Okay, so, I need you guys, let's do it the way we're used to. Here's y. Sine y is x. So we put this x over 1. Where would x go? Where would x go? Why did I put y here? Let's start there. Because that's the freaking angles. Now, where does x go? Because we know what sine wants from me. We know the ratio sine is. Yeah, over here. Good. The y side? Or the opposite, sure. And where's 1 go?
On the bottom.
No.
I mean on the hypotenuse.
Yes, because sine is the y side divided by hypotenuse, yes? You guys with me? And then, of course, what I need for my derivative is cosine y. So what do I need to figure out?
Pythagorean theorem.
Sure, I need old Greek dude to help me get this side because that's what cosine is based on. So what would this side be?
Around x squared plus 1.
Be careful.
9.
It'd be 1 squared minus x squared is this. So I get 1 minus x squared. So this is 1 over the square root of 1 minus x squared. Is that like a nice function? I like the hesitation. This is perfect because nice is such a subjective thing, but that's not a function I would choose if I could choose a function to work with. So that's not like a nice function, which makes sense because freaking inverse sine is not a nice function. It's a freaky ass function. In order for it to exist, we had to chop entire sections of sine off just so it would exist. Of course it's weird. So I would expect the derivative to be a little weird, and that's a little weird. If that makes sense. Okay. Love you guys, I love you guys. Now there is a different way to do this that I never thought about, but I think I thought about it right now because I just spoke to you guys about this. But it's not that big of a deal. But if you just take this and do dx dy, do you see how I don't even have to think about it? Dx dy would be equal to cosine y. And then I figure out what cosine y is, and then I just flip this and I get the same stupid answer, yes? Okay, sorry. That's not a huge thing, but I just never thought about it, and it makes me excited when I see something in math that I hadn't thought about. This is not one you have to memorize necessarily. You can if you want to. Okay. So here, let me see. Can you guys entirely on your own figure out the bless you, arcsecant? The inverse secant derivative. So I want you to figure out that guy's derivative. Replace h with y, actually, if you don't mind there. It makes it a little bit easier to work with. If you get stuck, it's a great time to get stuck because this doesn't really affect you grade-wise at all. So just do as much as you can. Give it a try.
So first, set it up, right? Then multiply by secant. So that cancels. Huh?
Take the secant of both sides. You're not multiplying.
Take the secant on both sides.
There you go.
That cancels out. Then on this side, you're left with secant y. And then, what do you call it? Over here, you're just left with x. And then you find the derivative of x, which is just 1. And the derivative of.
Yeah, what kind of sucks about secant with its derivative?
It's secant squared. Secant times tangent.
Tangent.
Yeah.
It's got no co, so it's not related to co. Derivative of x is 1. That's crazy. The derivative of secant y.
Secant y tangent.
Secant y tangent y, good start.
dy.
dy dx. Now, one really nice thing, though, about this is we know what secant y is, don't we? What is secant y? X. We told ourselves that right there. So I know exactly what to put here. The only thing I don't know is what tangent is, and I've got two ways to do that now. I could do the representative triangle way, or I could use tangent squared x plus 1 equals secant squared x. And I can solve for tangent. It's up to you. Go ahead and try to do one of those two things. If you don't know how to do either one of those methods, call me over. Otherwise, just pick the one you like better. Go for it. If you have no idea what the shit we're doing right now, call me over. I'm fine with that. I can try to help you. See what the hell crazy ass Jeff is doing. is kind of silly. Okay, that is true. So if I do it the representative triangle way, secant y is x over 1. Secant is 1 over cosine, so that means this is going to be x, this is going to be 1, which makes this the square root of x squared minus 1. If I used an identity, Jeff, you could do it. Tangent y would be the square root of secant squared y minus 1. Yeah, it's the same thing. We got the same thing. That's crazy. Because what is the tangent of y from the triangle?
Rad x squared.
Yeah, it's just that over 1, which is that. So this is 1 over secant y is x. Bam. Tangent y is rad x squared minus 1. If you guys had to guess, what do you think the derivative of cosecant inverse x would be?
X rad x squared minus 1 over
Do it again.
x rad x squared minus 1.
No.
Is it 1 over?
No. What's the derivative of just secant x? Secant x tangent x. What's the derivative of cosecant x? Negative cosecant cotangent. So a really good guess would just be put a negative on that. Because all the coshits got negative answers, yes? Okay, so not to put us through all of them, but just to show you. Here are the other ones. Do they collect them all together? I think they do. There they are. Here's the one we just did. There's cosecant. Do you see how it's just got a negative on it? Yes? I don't know if you guys can see that. Tangent we did earlier, inverse tangent we did. Look how inverse cotangent, what's the only difference? Got a negative, yes? So if you did have to memorize these, it also has that inherent symmetrical structure, right? But for me, the only one I really ask that you memorize is this guy. And we can always just look these up when we need them. Okay. Part of the reason I do that is because I don't have these other ones memorized, to be honest. Which tells me I didn't need to. So, that must not be important. Okay. I never make you memorize more than I have memorized myself. Okay. Now, I want to take a quick check-in because we've been doing a lot of weird shit recently. Basic derivatives are nice. The derivative of x cubed kicks so much ass. Everything we've done since then has been either based on limit definition of derivatives, which is just algebra, which we all believe in, or we built it from things we already knew. Implicit differentiation we created, we now believe in thoroughly, we can see that it works. And it allowed us to investigate weirder functions. So everything we've done, even I don't care how weird the derivative looks, it's just the result of things we know already. We proved before what the derivative of secant was, and we have implicit differentiation. Put those together, we got here. So I always want to stop and make sure students understand that this isn't all just built on nothing. We're not just going, that sounds good. No, it's built on stuff we proved before. So we can kind of let go of limit definition and try to base things on stuff we've already proved. Okay. Pretty sure that finishes section 3.6. I'm not misremembering. Yeah, I'm pretty sure. Okay. One thing I want to come back to is, can somebody help me with this? What if I wanted to take the derivative of the natural log of x squared minus 4 over, what you got, Jeff? X squared, let me think. Sure, plus 10x plus 16. Do you want to directly take this guy's derivative?
No.
Do you understand what that would entail? Right, well, what's the derivative of natural log of something?
1 over x.
1 over that. Times chain rule. Derivative of this would be what? A quotient rule, yes? So there's two things we can do. What are the two things we could do?
Factor.
We could factor and hope to God something dies. Yes? And then we could do something even more after that. So let's see. How do I factor any of this business?
X plus 2, X
Yeah.
plus 2.
And on the bottom, I'll get x plus 2, x plus 8. Is that cool?
Yeah.
All right. Of course I did because I made it. And then these die. Yes?
Yeah.
We say, thank you for dying. And then now my function is this, which is still kind of gross. But what can I do from here? I still haven't taken a derivative yet, right? So I'm not going to put a prime yet to confuse future me. What's the last thing I could do before I take a derivative?
Split it up.
Yep. No, get out of there, plus. Now, when I take a derivative, what do I get?
X minus 2, 1.
And notice, yeah, I'm not done with the derivative, but let me make a point here. Somebody semi with me. Factor, because it kind of looks like something that could reduce. Reduce if I can, and then use properties of logs to break it up. So this is an example of simplify before attacking with calculus. If the inside function, let me see if you get the one I'm about to say. If the inside function is linear slope 1, chain rule is not going to show up because the derivative of linear slope 1 is 1. Those are both linear slope 1. But if I think chain rule, the derivative of x minus 2 is times 1, okay, great. And then 1 over stuff, derivative of x plus 8 is 1, so times 1, I'm done. So will I put this on a test and somebody's going to start here and start doing a derivative? Yes. What can I do about that? Nothing. And they'll go, why'd you make it so long? Oh yeah, I didn't. If you just do this. So again, simplify before you try calculus. Just take a quick moment and go, anything in this that I could simplify? Yeah.
So what derivative were you finding last time?
Derivative of ln. What's the derivative of ln stuff? 1 over stuff times derivative of stuff. So if I said what's the derivative of x to the n, you would say n comes down, goes down by 1, right? And x to the n. What is the rule for natural log of x? 1 over x. If I marry that with chain rule, it becomes 1 over stuff times derivative of stuff. Do you guys start to understand? Chain rule is independent of the function that's at hand. Chain rule just says, hey, if you got inside, it gets a term. That's all chain rule says. I don't care what the function is. Okay. I love you guys. So, today's very exciting. Who was here yesterday? Who remembers what we're about to get into? Yeah. Sorry. Every math class is going to be. So, obviously, I would hope most of you guys are going to some kind of STEM path. Otherwise, what the hell are you here for? If you're going down a STEM path, you're very likely going to be doing something science related, potentially business related, which is still economics, which is the science of finances. But all these kind of things, what are they all predicated on? They're all predicated on actual real life observations. And what does that translate to? Which I really hate. It translates to word problems. But all word problem is, hey, great, look at you. You got calculus, great. How the shit would you use that in this situation? That's what this does, and that's the heart of what you're here for. I'm not going to make this more palatable, but let's see. This is not the word problems yet. This is stuff you need to be able to do before we even start setting up word problems. So I am going to, thankfully, shut the hell up. And I want you guys to do as much of this. Oh, did I give this to you already? Yeah, I gave you that. Oh, this one. I wasn't sure which one I gave you guys. All right, so This is not like standard fare. This is not like, well, this is like the third week of algebra. No, this is stuff you've been exposed to. And some of this is just not even math. Just can you draw what's happening? So go ahead and do what you can. Try to do these problems. You can work with people near you if you want to. Call me over if you need some help. What is, before you get too far, does anyone know what the angle of elevation means? Yes.
Is it not like the way you look up, like for example, if I was looking up there, the slope of the way I was looking up would be the angle.
Totally. So here's the way to look at it. If I look straight out, that's 0 degrees. Yes? Last semester I had a moment when I was, so why not relive this embarrassment? Were you in that? So it's like, if you look straight out and you look up to the top, and somebody would start laughing and realize what I just done in Elon. But if you look straight out, then I decide to do like this. If you look straight out and then I see a UFO up here, I'm in a plane altitude. That angle that I just went through is the angle of elevation. If I'm on the ground and I see that plane and I look up, that's the angle of elevation. If I'm in the plane and I see a person, you're not going to believe this. Straight out is still 0. And when I look down, that's the angle of depression.
Really?
Angle of elevation, angle of depression. Yes? Alright, so go for it. Try to do number 1. Now that we all got to relive a Musk moment. Number two is just a bunch of plugging and chugging, but when you first click the stopwatch, the plane is directly overhead. So if this is me looking straight out, the angle of elevation would be 90 degrees, yes? It's directly overhead. If I let 1 minute go by, the plane is traveling east, so it's going this way.
It's up 5 miles.
This is still 3 miles, yes? Yeah, what did somebody get for the distance the plane has traveled?
5 miles.
Yeah, after 1 minute, because it's going 300 miles an hour. So 1 minute is 1/60th of an hour. 1/60th of 300 is 5 miles per minute. Are you guys at all with me? So there was, like I told you, there was a bit of unit conversion. 300 miles an hour is 300 miles per 60 minutes is 5 miles per minute.
If you just do 300 divided by 60, wouldn't that be easy?
That's basically what I did. But the way I did it explained why we did it. Yeah. So 300 miles per hour is 300 miles per 60 minutes, which is 5 miles per minute. So after 1 minute, the plane's gone 5 miles, and the angle of elevation would be here. So if you wanted to, you could actually turn your triangle around and make this the triangle. This would be 3, this would be 5, and then the angle is actually living inside your triangle, and you don't have to do any weird transversals of parallel lines bullshit. Okay. You guys don't, you didn't have to draw your picture exactly like mine, but did you have the components there? After 2 minutes, what's the only difference?
It's 10 miles instead of 5.
Yeah, now this is 10, the shadow of the plane. What has happened to my angle without even calculating the angle? What has happened to it?
Increase.
It did what?
Would not be increase.
Hell no. Imagine looking at a plane. You see the plane is like almost overhead. Now let it go forward a little bit. What's happening to the angle here?
It's decreasing.
Decreasing. Yes? And of course, if I let it watch and then it goes to the horizon, eventually it becomes basically 0. Okay. That would require really good eyesight, which I don't know. How are we all feeling so far, you guys? All right, real quick. Can we figure out the angle from these pictures? And that's what I want you to do for part D. So can you finish out part D if you haven't done part D yet? I actually want to know what the angles are, and I want to know how much they changed.
We can use the.
You could use some beautiful.
The sine.
What kind of triangles are involved? Right triangles.
The,
Considering I would have to do more work to figure out the hypotenuse, I don't want to use a trig function that requires me to know the hypotenuse. Could you? Yeah. Why would you? I don't know. What trig function relates what I already know to be tangent? Tangent's x over y. Y for x. Good job. So then I can just do tangents. Okay. And I got calculators that I need to borrow one. Some of them even have battery power. Does everybody notice there's no calculus in what we're doing right now? Part D is sort of getting in the direction of calculus, but it's still not really calculus yet. I'll call this theta 1, I'll call this theta 2, just to make it easier. So tangent theta 1 is equal to what?
5
Careful.
3 over 5.
3 over 5. Y over x. Opposite over adjacent. Yeah. And then theta 1 will be the inverse tangent of 3/5. Did anyone do that? We could do degrees here, is fine. I think. Should I do degrees? It doesn't matter. Oh, you're the one that's almost dead. Poor little dude. What am I in? Yeah, sure. We'll do degrees. We'll do radians too, I think. Let's do that. So, yeah, let's do radians. Screw degrees. So I get 0.5404 roughly rads after 1 minute. So ready, please? So after 1 minute, the angle is about 0.50404 radians. And after 2 minutes, what will tangent theta be related to now? Or be equal to? 3 over 10. So then if I throw in the calculator inverse tangent of 3/10, I get... what do you guys get? Anybody?
60. Zero's not that.
Hmm?
Or, oh, well, I get degrees.
Oh, okay.
0.2.
2915 roughly. So then how much did the angle change by?
The difference between us.
0.34 something 89? 3489, I think. Oh, good job, Jeff. So it changed, the angle changed
0.2489.
by 0.2489 radians. Okay. All right, so we're just going to hold on to that. Obviously, as the plane moves forward, my head's going to kind of come down. The angle from straight to up is going to go down. Okay. If I wanted to draw this at an arbitrary time after the plane was directly overhead, what parts of my picture are changing over time?
The distance.
Which distance?
The x.
Yeah, this distance, the shadow of the plane.
Yeah.
So if I wanted to draw this situation, but I wanted to do it, where am I going to do this, Jeff? I would say this stays at 3. Yes? This distance is changing over time, and this angle is changing over time. Yes? Okay. So this is an example of snapshots in time. I take a snapshot at 1 minute and I can see what's going on. I take a snapshot at 2 minutes, I can see what's going on. This is the behind the scenes controlling everything what's going on. The 3 miles stays constant. Any flat earthers out there, this is local enough that it don't have to consider the curvature of the earth. Okay, look, okay. All right. So we are going to do a calculus problem here in a minute that involves this, and we're going to verify something that we found here. Number 2 is a little more straightforward. But I wanted to introduce this idea and to get your guys imagining this happening. Have you guys ever been to, like, the place I know that you can do this is in Balboa Park, the Spanish Art Village? You guys ever heard of that before, the Spanish Art Village? And if you go there at the right time, or at least this has been a while since I saw this, you can actually see them blowing glass and making different shapes and so forth with it. And it's insane. They got the little oven, they open it, it's stupid white hot, it's crazy. Anyway, sorry, it's just so. So can you imagine, has anyone never seen glass blowers in action? YouTube that damn thing. It's the neatest thing to watch this molten glass like being blown and then they let it cool and then, you know, it's just kind of neat. So I've got this long pipette and at the end is this glass and I'm blowing into it and the glass is actually expanding because I've got the glass hot enough that it's basically liquid. So it's expanding like a soap bubble. And I'm blowing air. Somehow I am a master glass blower and I can control my breath so well that I'm doing exactly 2 pi cubic centimeters per minute. So just deal with that fact. Prove I can't do that. Can't prove it never, sorry. This one's much more straightforward. There's no pictures to draw. Go ahead and do this real quick for me. And this is just a bunch of plugging and chugging. Part B might be a little more interesting, but actually, and part A, well, let's see what you think. I don't know. Did I forget something? What do you think? No, I didn't. Okay, good. Assume the volume at the beginning is 0. So I haven't blown anything in there, so still there's no volume to this little thing of glass, and then I blow into it. It makes sense. Okay. Just to make sure everybody's with me on this, does everyone understand there's 0 work to do on part A? If it starts at 0 volume and I let 1 minute go by, how much air did I blow in there? Yeah, so that's going to be the volume after 1 minute. It's going to be this, 2 pi cubic centimeters. This is where the work's going to come into play. Okay, go for it. There's a few assumptions. Just to help out a little bit. V equals, and you have a formula for V, so then this one just becomes a solve the equation kind of deal. Yes? Okay. Oh yeah. So just make sure everybody's on the right track for part B. We know the volume is 2 pi. We know the formula for the volume is 4/3 pi r cubed. I can solve for r by multiplying both sides by the reciprocal. You can do it, Jeff. It's just solving the equation.
Isn't it?
So then you get the cube root of 3/2, which is roughly something or other if you plug it in a little calculator. Oops, no, I don't want that. Yep, there we go. I get 1.145 roughly. And that would be centimeters. After 2 minutes, what's the volume?
4 pi.
That's crazy. Because I blew 2 pi more cubic centimeters in there. And then we do all the same shit, but now that the volume is twice as big, that means that, well, let's see, if I make that a 4, let's just do it, Jeff. 4/3 pi r cubed equals 4 pi. The 4 cancels, the pi cancels. Multiply by 3, take a cube root. Cube root of 3 is roughly 1.442. And I just noticed I asked kind of like the wrong question down here because that's kind of a stupid question, but how much did the radius change?
Point 303.
It would be 0.297, I think. Let's see, 1 point. Yeah, 0.297. Not cubic. Okay. So the radius changed by about 0.297. Okay. Nothing amazing there. So we're still talking about calculus ideas because you can see a slope in here, yes? For the minute after the first minute, the rate of change was 0.297 centimeters per minute. You guys see that? How much did the radius change from 1 minute to 2 minutes? So over the course of that minute, it changed by 0.297 centimeters. So what's the slope approximately at 1 is 0.297 centimeters per minute. Now, if we use calculus, we can figure out exactly what that slope is. This is not perfect because if I use a graph to make a prediction about where I'm going to be. So let's say I'm right here. And I'm like, okay, I know the slope right here. And I make a prediction where I'm going to be wrong, yes? The further out I try to make that prediction, I'm going to be wrong. Because the instant I move away from this point, I'm now at a different slope. So we've already talked about this a few times. If I try to use calculus and I try to make a prediction too far out, I'm going to be potentially very far off. In Calc 2, we actually learned how to use more calculus to get this estimate to become perfect for certain functions. But for us, all we can do at the best is this straight line approximation. Okay. I love you guys. We're doing really good. Okay. You're enjoying this, which is good. One more thing I want to do before I do this next handout is I almost made some stuff for the back of this. If you just turn that sheet over, can you guys remind me how to figure out something like this? Let's say this is 8 inches, and let's say that this is 2 inches, and let's say that this is 1 inch. Can anyone figure out what this length is?
Yeah.
What idea? Does anyone remember the idea I'm not ever as interested in you knowing the words for something as being able to do the problem, but does anyone remember the idea?
It's like a smaller triangle, a big triangle, but then the size.
So the word smaller has a lot of the letters I need in the right word that I want to hear. Similar. So this is similar triangles. Do you guys understand how this triangle is just a smaller version of this triangle? And when I say smaller, I mean literally just zoomed out. Right? So just a order of magnitude smaller. Yes?
Don't you make it a ratio?
Make a ratio. So similar triangles is one of the first geometrical concepts you use when you learn proportions. You go to similar triangles very soon after you first learn proportions. So what proportion can I make? There's several ways to make proportions here. They all come out to the same answer.
2/8.
So you can take big to big. I like it. So big triangle, the big triangle y side to the big triangle x side has to be equal to
1/x.
the small triangle y side to the small triangle x side. Yes, of course. I love it. Now you could also do y side to y side equals x side to x side. Why are those the same? Is it, Jeff? Did you really do that right? I think I should have, yes? Yes, I did. Good, good. Why are those the same? Because when I cross multiply, for one thing, I get the same thing, 2x equals 8. 2x equals 8, yes? And if anyway, there's a few different ways to see how those are the same thing. Okay. So it almost doesn't matter how you choose to write your proportion, as long as you have the right relationship. So if you designate this to be big triangle y side to big triangle x side, this has to be small y to small x, blah, 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 blah. Either way you do this, what do you get for x?
X equals 4.
That's crazy. So there's the idea of similar triangles. Similar triangles shows up an insane amount of the time in the kind of problems we're about to get into. Not every problem, but a decent amount of the time. And it's something that we sometimes forget exists. So, let's do this. Actually, let me start with a simpler example, yeah. Here's what we're about to get into. Has anyone ever thrown a rock into a pond?
Yeah.
Okay. And I always like to joke about, there's some fascination that young kids have about, and I still have the fascination, about throwing stuff in the water. It's just, we're fascinated by that. Especially if it's something that's going to explode when you throw it in the water. And that is how I say the word water, by the way, so just have fun with that. What happens, of course, when you throw a rock into a pond? Besides, the ducks kind of like, wonder what the shit's wrong with you. Yeah, you get this ripple effect coming out, yes? And of course, what shape does that take? Circle. It's crazy because it makes sense because physically it should emanate from the same in all directions, yes? So let's say we throw a pond into a rock. Sure. Why not, Jeff? Throw a rock into a pond. It creates a circle, circular ripple, where the radius is growing by 1/2 inch per second. That's decently fast. So do you guys see this in your mind's eye? Can you guys see this? We throw a rock, we make this ripple, and it's growing. The radius of that ripple is growing at 1/2 inch per second. So can you see how you can take snapshots of the situation? I could make you do all the same shit we just did. If I wait 1 second, what would the area be? Well, after 1 second, the radius would be 1/2. We could do the area formula, we could do the area. After 2 seconds, blah, 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 yes? Can you draw the situation after an indeterminate amount of time?
No.
Too bad. That's going to suck for you. Of course you can. Of course you can. What's the shape going to be? Oh my gosh, I just had my 8th puberty. The shape's going to be a circle. What are the important parts of that circle? Well, in this case, it's really only 1.
The radius.
The radius, and of course we know that because the problem, it's a circle for one thing, but also the radius is spoken about. If the problem is a diameter, I would have put the diameter in there. Okay. This is at some indeterminate time, yes? So what do I put, how do I label this? The circle is judging you on that. No. What's the area of that circle?
Pi r.
Do it again.
Pi r.
What is it?
2 pi r.
That's circumference.
Pi r squared.
Pi r squared, yes.
Always got confused.
Now, let me stop right now. One thing is, you see where I'm going? What do you think a question I'm going to have for you might look like, roughly?
Find the radius at a certain point.
That's too easy, right? If I said wait 7 seconds, then you can know what the radius is without thinking about it. I want to know some of the area at a certain time, yes? Which means I gotta somehow incorporate the changes in the radius. Okay. Can you guys agree with me that what I've written down so far there is a relationship between the area and the radius? Y'all agree with me there?
Yeah.
Okay. I'm trying to show you why we call this section what we do. This formula relates the radius and the area. If I took a derivative of that formula, I would get a relationship between the rates of change of area and radius. What's the name of this dumb section? Related rates. That's why we call it related rates. So if I set up a relationship between variables in a situation, and then I take a derivative, I get a relationship between the rates of change of everything in that situation. Really want you guys with me. I know, I don't know, from your perspective, is it often like, oh, this guy's just up there speaking a lot of damn words, just show me how to do it wrong. All the words I'm saying is helping you understand why the problem works the way it does. So, this one was easy. This formula is nice. Thank you, formula. Are they always going to be easy to set up? Hell no. This one was nice. Now here's the trick. What am I going to take the derivative with respect to? What am I letting go by? No, come on. Time. We are letting time go by. So here's where this is different from straight up implicit differentiation. How many variables are in that function I'm looking at? 2. But what are both of those variables changing as a consequence of? Time. I'm going to take a derivative with respect to time. Now, let me ask you this. Is the radius changing over time?
Yeah.
So is R a function of time?
Yeah.
Is the area changing over time?
Yeah.
So is A a function of time?
Yeah.
So here's the trick. With implicit differentiation, I only put dy dx when it was a y piece I was looking at, yes? Because that's the function of x. So A and R both are functions of time. I'm going to have a dA dt, and I'm going to have a dr dt. Every freaking variable is going to have a little tack on like dy dx. Because every variable is a function of time. So here, I'll do this side. Okay. So I want to take the derivative of both sides with respect to time. So how does this work? What rule am I going to have to use here because R is a function of time? Chain rule. So what's the first step of chain rule?
Derivative of something. Derivative.
Yes, derivative of something squared.
Something times
What's the derivative of something squared?
2 something.
2
2 something.
comes down? Yes?
Yeah.
Times
Something
derivative of something. All right, let me just stop for a minute. By the way, I want you to notice something interesting that I make a big deal out of in math in Calc 2. What was the formula for the circumference again? 2 pi r. What's really neat is if I put a piece of tape around a circle didn't I just add 2 pi r to the circle? So how much does the area change if I change the radius by one little bit? It changes by 2 pi r. So derivatives of volumes are areas. Derivative of areas are lengths. We don't have to understand that right now, but it's interesting that see 2 pi r is the freaking circumference. There it is. It's right there. So when I teach a certain, well, actually later this semester I'm going to bring this back up. That's right. Every now and again, remember where the hell I am. What do I know that's in this equation right now? Do we know anything?
Yeah.
What do we know?
Radius.
No, we don't know the radius at all. What is this in terms of the variables we chose? What is this? Inches per second. So what is it? Go ahead, sorry. dr dt is how the radius is changing over time, yes? If I wanted to know how much the area is changing over time, what one more thing must the problem tell me? We have this, don't we? Can I get what the, yeah, I need to know what the radius is. So the way, let me just stop. Please do not, Jeff, just stop. If I have an equation that relates variables, and then I take the derivative, I get a relationship between rates. Therefore, if I directly make an observation of one thing's rate of change, I can then use an equation to figure out how much another thing's going to change. Is everybody with me? Depending on the level of difficulty of the derivative, I will sometimes get these other kind of things left over. The rate at which the area of the circle is changing depends on what the radius is right now. If I have a bigger circle and I move it out 1 more inch, I'm going to get a lot more area. Maybe. So we can't currently do this. It's not our fault. The problem didn't give us enough. So if I add on here, here's the question. Find the rate of change of area at a time when the radius is 6 inches. Sure. Can you now do this?
Yeah.
Because I know everything in the related rate step except for dAdt, which is what the question wants from me. So now it's just plug and chug, right? What did I put in there? dAdt equals 2 pi times,
6.
that's crazy, times 1/2. So then I get 6 pi square centimeters. Or roughly 18.7 cubic square centimeters. Do you guys see how r equals 6? Could somebody tell me how many seconds that is?
3.
12, because it's increasing half an inch every second, yes? So to get to 6 inches, it would take 12 seconds, yes? This is a snapshot. If I would have said r equals 8, that would have been a different snapshot, yes? So when you hear me later say snapshot, you know exactly what I mean. Okay. How do you guys feel about this so far? This equation, did we have to create it? No, it's just a known equation, correct? One thing that students really dislike about word problems, and I don't blame you because you don't get enough practice with them anymore, is when you have to create your own equation out of a situation. Okay, so we're going to look at some of those. So here, I don't think I've given you this to you yet. No. Let's do this here. The first 2 problems should sound very familiar.
Let's go.
Oh, you already have
What did you do yesterday?
I was reviewing, MLT open coursework. I was reviewing one of the courses for C and C++. So
Huh? Oh, I did? Oh, neat.
set up an IDE.
Oh,
You know what
I mean,
IDE
I
is?
don't
You
think
run
you
one
want to
computer
do
science.
Yeah.
And you get a development environment.
All right, guys. So, let me try to figure out how I want to do this. Can you guys do 1 and 2 sound very familiar? Yes.
It's the same.
But they have more information now, yeah?
Yeah.
And they're asking for more. Can you guys redraw? Remember, I showed you how to draw this problem. Here's the mistake students make. Can somebody tell me what information is in the problem that's related to the snapshot?
One point.
Yes, 1.5 minutes. That's related to the snapshot. Is everybody with me?
Yeah.
So I don't want to put that into my picture. My picture has to represent any time. If I put a specific number in too early, what am I going to get for the derivative of that piece? What's the derivative of 1.5? 0, or whatever the mileage would be. So, can you guys redraw the general picture that I gave to you before? All right, what are my 2 variables that are going to be involved in this?
3 miles.
No, it's not a variable.
There you go.
So 3 miles is part of this. It's going to be part of every triangle.
Altitude.
Theta. Altitude is 3 miles. That's constant.
Oh, the
And what else is changing? The plane is moving, so the shadow, yes, the x. Okay. So this is not going to come into play at first. I'm not going to worry about him until way later in the problem. Never put the snapshot information into your original picture. Everything that's changing over time needs a variable. So what do I know is not changing over time is this. So I can put a number there. That's completely valid. It's not changing. This is changing. This is changing. I'm trying to show you the mistakes students make, and I understand. If I were you, I'm looking for anything that's concrete. I'm like, just tell me something for, oh, thank God, I know 1.5 minutes. Too bad, don't use that yet. You can't use it because everything's changing. They're going to feed into the derivatives. Now, here's the trick. This did not come with an easy relationship. We have to tease the relationship out. Of course, we already know what the relationship is. And we can pick it. So, what relates the various elements of my general picture? What relates the variables we've identified and any constants?
How far you can.
No. What function relates these elements? Trig, yeah. Which one do you want to use? We're the humans here. We can use. Give me one. Okay, let's look at tangent for a second. Let's look at tangent for a second. What would the tangent theta be?
3 over x.
Is that an ideal place for your x variable to be?
No.
So, the point I'm going to try to make right now is to remind all of us, we're the ones who are members of the species that created that shit. We don't have to use that. Do you see? You could. It would work. It would work beautifully. But do you see how it's worse than it has to be? Because the x is on the bottom, which makes it x to the -1. So what might be a slightly better trig function to use then? The only other one we could, cotangent. So look, I'm going to try to do it both ways. Why not? So have I got a relationship set up between all the variables and stuff involved in the problem? Yes. What can I now immediately do? In fact, before I go there, have we got variables defined? Yes.
Yeah.
If I look at this, what is this related to? X. That is related to x. How? That's not what x equals, right? Well, what would 300 equal?
The slope.
Good. So give me the symbol for what it is. What is 300 the rate of change of?
Over hour.
No, what's 300 the rate of change of? Good. So what symbol would I put there for rate of change of x over time? dx dt. Kick ass. So you've identified for yourself where the shit to put 300 in the future. You're going to put 300 wherever you see dx dt. If you need to. Because one way or the other, we either have to or no. It doesn't matter for this specific problem. What's the question asking me for? In symbols. I should put it up here. So let me put dx dt is 300. What's the question asking me for in symbols? d theta dt. Okay, good. This is the step that when I teach like intermediate algebra word problems, students skip that step. And that step is the dumbest one to skip. Defining for yourself what you know and what you're looking for. Why is that good? Well, so I know where to put 300 then. And I know if I don't see d theta dt in the thing I'm working with, I know it's not good. Because how can I solve for d theta dt if it's not in the equation? So if I use this one, let me rewrite this a little bit. All right, let's just use this one for the moment, and then we'll try it this way. What am I going to do now? So that I can use the information I know and get the information that I need to know. Take a derivative. Every variable now is affected by chain rule, because every variable is a function of time. So what's the derivative of tangent stuff?
Secant squared.
Secant squared stuff, and then times
Negative 3.
d theta dt equals, if that's on the other side, careful. So what's inside the tangent? A function of time. So it's tangent stuff, derivative is secant squared stuff times derivative stuff, yes?
Because
Chain rule, totally. Over here, go with what you were just saying.
Negative
Negative 3, x to the
x to the negative 2
negative 2,
times
dx dt, kick ass, because the inside function is x, yes? Do you see d theta dt in the equation we got?
no.
Yes.
Oh yeah.
Do you see dx dt in the equation we got?
Yeah.
Which means I know what to plug in there. Do I have to see this? No, I don't necessarily have to see it. If I do see it, I know what to put there, yes? Okay, I really want you guys with me. So, what do we not know that this needs? Say again? No. All right, d theta dt I'm cool with not knowing, because that's what I need to solve for. If I'm trying to solve for d theta dt, I better know every damn other thing. So what's something else I have to know that I don't currently know? Don't know x. How could I get x?
Oh wait. Oh.
How many seconds have passed?
Well,
1 point. I'm sorry, not seconds. Minutes. How many minutes have passed? 1.5. Yes. How fast are we going? 300 miles per hour. Can you guys take a minute and figure out
5.
how far we've gone? It's 5 miles per minute. Yes.
So 7.5.
7.5. Okay. So remember earlier we figured out this is 5 miles per minute. If we go for 1.5 minutes, that's 7.5 miles. So x is 7.5. I really dislike this way, but we'll be okay. This way will be much better. What else do I not know that I need to know? I don't know secant theta, right? Do we know what x is now in the snapshot? 7.5, yes? So x in the snapshot is 7.5. Could you figure out what secant theta is then?
Yeah.
What am I, all right, let me stop for a minute. This is where students understandably start to disassociate. You're sitting there, you're going, no, I'm just gonna worry about this later. There's kind of a lot of steps. Do you guys agree? And I really hate the word problems because it's just freaking real life shit. What do you hope math is going to do for you? Help you with actual real world shit, yes? Now this is a very silly example, and word problems almost always are. I like to joke about where else but math could you buy 60 cantaloupes and nobody worries what's wrong with you? Right? You and Fred goes and buys 60 cantaloupes. What's going on with Fred? What kind of a weekend has this guy got? He loves cantaloupe, I'm going to leave him alone. Yes? Or the guy that forgot how much money they put in the bank. I forgot how much money. I'm like, what a great problem to have. How much money do I have? Sorry. I don't know if you guys remember making word problems in algebra, but they're always a little silly. Alright, same thing happens here when we're first learning, because we don't know enough math to do a lot of freaky real life problems. I need to figure out secant theta. What am I missing to figure out secant theta from this triangle?
Hypotenuse.
Hypotenuse, good. How do I get the hypotenuse? Ogre. I love it. Right? So let's get an approximation for that.
Right.
Yeah, it'd be 9 plus 7.5 squared, square rooted. Holy shit, Jeff. Try it again. There we go. I get 8.0777. Actually, let me just do this. 9 plus 7.5, and you'll see why in a minute. This is the square root of 65.25. All I did was stupid Pythagorean theorem, yes? Why did I write it like this? Because what does this problem actually need? Secant squared, yes? All right. What's the secant of theta?
Square root of 65, so,
Yes, because secant is 1 over cosine. Cosine is x over h, so secant is h over x. But I want to square that. Do you see what I mean? Okay. Someone's like, just do it, Jeff. All right. If I square this, I get 65.25. If I square 7.5, I get who knows? Jeff, that's why. Oh, there you go. Did I write? Oh, I did. Okay. So we figured out what secant theta is. I squared it. D theta dt we don't know, which is fine, because that's what we got to figure out. We figured out what x was. We know what dx dt was from the beginning. And now I can figure out, let me think about something for a minute. Yeah, this will work. Yeah, okay. All right, so what is d theta dt? Now the only thing with this is, can somebody see what units this is gonna be in? This is where I have to be a little more careful. Nothing wrong with what I've written. No, this is definitely gonna be radians, but radians per what?
minute.
No. Radians per hour. So if instead of 300, if I put 5 here, that's 5 miles per minute, now it'll be radians per minute, which makes more sense, because everything else is in terms of, the other thing is in terms of minutes, yes? What's something else in terms of minutes? Oh, just the fact that we have 1.5 minutes, that makes sense. So if you leave 300 in there, you're gonna get per hour. If you leave, if you put 5 in there, you're gonna get per minute. So it's a total choice for us. So I'll put 5 in there just because. And now I just have to throw all the shit in the calculator. If I solve for d theta dt, I'm going to multiply both sides by the reciprocal. I just got to throw all this shit in the calculator. Bah! These two actually kill each other, which is neat. Die. I don't know if you guys see that. Let's see, negative 15 over that is roughly, who knows, Jeff? 3 over 13. Negative 3 over 13 is roughly, I don't know my over 13s. 7. About 0.23. I don't know. I'm trying to do this in my head. Negative 15 divided by 65.25 is, holy shit. Yeah, sorry, I just got that almost exactly right. Basically 2.3, yeah. Negative 0.23 radians per minute. Let me stop for a minute. Let me let you guys sit there and absorb that while I find my work from earlier. There it is. So right at 1.5 minutes, exactly at 1.5 minutes, my angle is decreasing by 0.23 radians per minute. Yes, you guys with me? You guys with me? What did we find before when I went from 1 minute to 2 minutes? How much did it change? And that's finding a secant line. 1 minute to 2 minutes. How much did the angle change by?
1.249.
Yeah. And I didn't put, I just said it changed by this much, but we talked about how it's getting smaller, so it should be negative, yes? If I'm looking at it as a rate of change. So this is an estimate of how much change I should expect if I let 1 more minute go by. How close was this estimate? Really freaking close. We got 0.24, whatever the shit. I already forgot. That's really good, especially considering the dumb function moves. The minute I move a little bit, the slope changes. So that's a really good estimate. Now, of course, it's not a very far way to go. If I try to estimate, like if I wait 10 minutes, I'm probably going to be really far off. The estimate gets really bad if I let this go for too long. I don't know if you guys are with me or not. I always like to show you. Very often we'll do a related rates problem, and we'll get an answer, and we'll go, ooh, neat. The concrete behind what we're doing is what we did earlier. You could see exactly how much it changed from 1 to 2 minutes. So if I do calculus at 1.5 minutes, which is a secant line versus a tangent line, I should get roughly the same number, which is exactly what just happened. And everybody goes, So what about number 2? Does that sound familiar?
Yes, Jeff.
Can you guys try to do the first few steps? Can you identify, well, the variables are kind of given to you. Can you write in symbols the question and write in symbols what you're told?
Is it dx over dt?
So, I mean, for example, what is this? And very often you can look at the units.
dx dt.
No, definitely not, because what's the top?
Centimeters.
Cubic centimeters. And what geometrical idea is that related to? What do we measure in cubic units? Volume. Because volume is length with height, yes? 3 dimensions, that's why it's cubic. So this will be dv dt is 2 pi. And what's the question asking me for, of course, in symbols? Not r. dr dt. So if in my equation I see dr dt sitting there, I'm happy with that. If I see other shit I don't know, I go, damn it. And then I gotta try to figure them out. So can somebody help me out? Do we already have the equation?
Yeah.
This problem is instantly that much better. I don't have to make my own equation. I already have the stupid equation. What's the next thing I would do? Oh, and real quick, what's the snapshot information? 1.3. So identify the snapshot information so you do not use it too early. If I plug a 1.3 in for r, my derivative is going to be 0. Nothing ever changes. We'll go back to living in caves. Don't make that happen. So what's the next thing you should do?
Plug the
Derivatives. Yeah. We have to get derivatives first. Yeah, go for it. Take a derivative. think after this problem, we'll take a break. Some of you guys are like, please, you guys. Yeah, please. This one's kind of nice, yes? Because dVdt, what happens over here? 3 comes down, kills a 3, makes it 4. Power goes down to
2.
Georgia. Oh, 2. Sorry, that goes down to Georgia. And then what's the inside? What's the inside of this function?
Radius.
So what do I have to tack on here?
dr.
Good old chain rule piece, yes? That's the easiest thing to forget. And it's understandable. So many days ago did we actually learn power rule? Not that long ago. And this is going one step further. It's going, hey, r cubed, r squared makes but r is a function of time. You gotta put the dRdt chain. Do I know everything I need to know? Do I know dvdt?
Yeah.
Yes. Do I know r? Yes. And this is fine. It's okay I don't know this. I don't want to know that yet, because I'm supposed to figure it out. So now, just go ahead, plug all the shit in there and figure out what dRdt is. Okay.
Yeah, let's call it. Just call it for my
1.3 squared is 1.69. Is everybody with me on that?
Yeah.
If you don't throw in the calculator too early, you can very often simplify shit and have less stuff to worry about in the calculator. But people often just start throwing things and getting all these weird decimals. I try to keep it to the very end to throw in my calculator. What are you guys getting here? Yeah, 2959. Yeah, so let's say 296 roughly. What would the units be? You never have to think that much. The top is radius and the bottom is time. So in this case, what's the length in terms of? Centimeters, and what's the time in terms of? Minutes. Okay. Now, not surprisingly, we did this problem. Right in between these two radii is 1.3. And what did we observe? How much did the radius change over 1 minute? 0.297. And what did we just get? 296. It's not exactly the same because slopes are only good for that instant, but it's a really damn good approximation. Almost too good for government work. So let's do this. Before we do part B, we'll take a break. We'll come back at 10 after, that's fine. If in the middle of that you need some help with something, let me know. Otherwise, go take a break. Get out of here. So, understand things have ramped up a little bit. Would you agree? There's a few different levels to this kind of problem. It could feel like it just came out of nowhere. So we've been focusing so much on learning an individual way to take a derivative of something. We learned power rule, product rule, quotient rule, then we learned how to take derivatives of specific functions and all that business. This is kind of like the penultimate place after algebra and the calculus. And we're finally saying, how could all of this come together and do stuff in the real world? I will admit, I said this earlier, these word problems are kind of lacking. And they almost have to be, just so they can be something we can work with. But very often, one thing this leads to is there's a class called differential equations that involves an equation with derivatives in it, and you're supposed to try to solve for the original variable. So it's sort of like the reverse of this in a way. So this kind of sets up the idea for understanding that better. We're just trying to undo what we do here, we're trying to undo it. Because very often the observations we make in the real world are observations of rates of change. And then we can see how those relate, and then we want to know, well, how do the quantities themselves relate to each other? We want to kind of do this backwards. But also, have you guys ever seen, they sell these things, and this doesn't happen a lot here, obviously, barely ever, but I used to live in Florida, and we had these things, these little crank radios, where if you crank it for a while, it'll actually generate enough charge so it'll work. In case the power goes out, you have access to like emergency information. So you could set up an equation and then take a derivative to figure out how quickly you would have to crank this to generate a certain amount of current. And maybe there's a device that will only work at a certain level of amperage, which is a certain level of current. You can figure out the equation and figure out how fast you gotta crank the damn thing and get it to work. So there are applications of this that make a little more immediate physical sense. These are beautiful, I love them. At the same time, they're a little lackluster at the end. You're like, okay, now I know that when the radius is 1.3 centimeters, this is happening. What would that mean for me? But there are other problems that involve a little more complication to them. So we have to kind of start with more basic stuff that doesn't immediately satisfy us for the real world. Okay, I just want to say all that. With all that said, this one, by the way, do you guys see? This is the surface area of a sphere. Did you see this show up somewhere else? Just like we spoke about earlier, the derivative of the volume of a shape becomes the surface area of that shape, or the area, in this case surface area, because it's a three-dimensional object. That's just a neat idea. How do we do part B? Why did I ask part B second? That specific question.
Because there's gonna be something that we need for part A.
Yes, because what did we actually get from part A? The rate of change of the radius. And this is a formula dependent on the radius, and I want to know the surface area. So I'm going to have to know the rate of change of radius. Okay, can you guys go ahead and try to do part B? The formula is given to you. I still give you the same snapshot information, correct? You can immediately start attacking this with calculus. Go for it.
Do you derive that?
Huh?
Do you derive that?
Yep. Take the derivative. Take the derivative. Differentiate. 4, 6, 10, 14, 16. I seem to be leaking students. This is everybody's favorite lesson. I will say, I told this to somebody earlier, there is another section of calculus word problems. They are always, students enjoy them more than this. This is a more complicated word problem than what we're going to face in chapter 4. That's kind of nice. We're doing the hard one first, so later we can enjoy how relatively simple that is. Has anyone taken this guy's derivative, or am I talking too much?
Yeah.
I'm talking too much.
8 pi r.
So S is 4 pi r squared. ds dt, which is what we need, yes?
Mm-hmm.
That's the question. Is 8 pi r
times dr over
dr dt.
or
Careful.
dt squared.
Yeah, because we're letting time go by, which is always going to be dt on the bottom. Okay. And this one's pretty straightforward compared to some of the other stuff we've done on this page. I didn't really have to take that. We know what dr dt is. The question is ds dt, and we can see it right there. And they give us r. Yes? So this is just a pure plug and shove. So just throw in the old calculator. 8 times pi times 1.3 times 0.296. We'll use that estimate, that's fine. And whatever the hell that is. 0.3, it's gonna be roughly 432 pi, it's gonna be roughly 96. I would say about, I don't know. I lost track of what's going on. It's roughly 99, maybe? Jeff, just do it in here, dude. Did you leave something out? You might have. Oh, okay. You guys get that? 96.711 roughly? No? Yes? No?
9.67.
96
I
point.
got the same thing. 9.67.
What'd you get?
9 point. Basically.
Oh, I left it. This is my fault. I put. It's 0.296, not 2.96. Yeah, 9.67. I'm with you. I think I did the same thing in my head. 9.671. Is that better? What would the units be? What is S?
Surface area.
Surface area. So that by itself would be what?
Centimeters squared.
Squared. And then it's over dt.
Which is time.
Time in this problem is minutes. Real quick, I want to really make sure you guys understand. This notation kicks the prime notation's ass when you have word problems where units are going to be part of what I grade you on. If you leave this out entirely, I'm going to take points off, and I'm going to be a complete dork and say sheep per century and put some, what did you mean? So please, don't make me do that. Put the units down. Okay. Do you guys? That was pretty straightforward. Look at number 3. This is the one I was prepping you for. We haven't used an idea that we talked about before we did the sheet. And this is where that idea comes into play. So we have a conical tank. Conical is just a neat word to say. Do you see how this tank is oriented? It's a tank shaped like a cone, but in order for the radius at the top to be whatever, so it's got to be like basically like a gigantic ice cream. Yes. The tip of it's down at the bottom. Yes. Go ahead and draw that picture. It does not have to be 3-dimensional. It's just, what would that look like if I look at a cone from the side? Looks like a triangle, yeah. Now if you want to make it 3-dimensional, you can make a circle at the top and then bring to a point, or you just make it a triangle. Either way, I don't care. They're both basically showing you the same thing. This one's looking down at it a little bit. This one's looking at directly straight on. They tell me, can you label the thing, what's not changing about this tank? The tank itself is not changing over time, yes? So what do we know that we can label on this tank?
The height.
Yeah, the height is 60. The tank height is 60 feet. It's not 60 height, Jeff. 60 feet. What else?
The 20 feet.
20 feet radius. Be really careful. I can't remember if any problems give you the diameter, but that's sort of a dick move. Just be careful when they give it diameter. You almost always need radius. Okay, that's the physical dimensions of the tank. Unfortunately for us, we're not curious about the tank itself. We're curious about its contents. Yes? One semester, a student challenged me to make a problem involving the fact that cats are liquid. Have you guys heard that theorem? Liquid is anything that takes the shape of the container you put it in. If you have a cat, you know what I'm talking about. They take the shape of the container they go into. So they're basically, there's a theory that says they're liquid. So I could have said that. I'm very sorry. We're letting this water drain out of here. And again, that's the way I say water. Thank you. For the sake of the physics of it, we'll say it's draining from the bottom. Doesn't really matter. Can you guys just pick an arbitrary starting position for where the water level is? Don't put it at the top. That's not going to be easy to label. So what do I mean? What do you mean, Jeff? Dear God, man.
Water level inside.
You could put it down here. That's kind of dumb. You could put it way up here. That's kind of dumb. I'm going to put it somewhere in the middle. There's my water level, or my H2O level. Is that where it always is?
No.
Of course not, because what's the whole idea? I'm letting water drain. That's the very first thing I said. So what is the height of that water? Water? I'll just say it like that.
60 minus the.
Don't overthink it. You're overthinking it. What's the height of the water? No.
20?
Seriously, everybody's overthinking it. Every single person here is overthinking it. What's a great letter for the height? Okay, the height of the water is H. All right. How high is that? H. Okay. What's the radius of that water that's in there? Still overthinking it. R. Just doing nothing but overthinking. So what variables are changing about the water? Its radius at the top and its height. As I let it drain, those two things are changing, correct? Are they independent of each other? Do you guys agree that at a certain height, the radius is going to be something specific? If I let the height change, the radius is going to be something else. So they are connected to each other, aren't they? Okay. One thing I did not put down here is the general formula for the volume of a cone. Does anyone know what that is? What's the volume of a cylinder? So a cylinder has got a circular top and then goes straight down to a circular bottom, yes? What's the area of the circle? Pi r squared. And the height of the cylinder is h. So what is the volume of a cylinder? Pi r squared times h. You guys with me?
Yeah.
There were these things called CDs. It's so weird that now, I used to say there was these thing called records, but now it's like, does anyone even know what a CD is anymore? I don't know. And if I stacked so many of them up, it's going to be the area of a CD times the height of the CD. That would be the volume that goes through. Are you guys at all with me? Just to push my luck here, any repeated shape. Has anyone ever seen a Toblerone?
Yeah.
Okay, if you don't know what a Toblerone is, go get one and eat it, and then thank me tomorrow, okay? So Toblerone is this, what shape is it? I just gave it away then. If I slice it, what shape does it take? Triangle, so it's triangular, yes? So if I knew the area of this triangle and I multiply by the length of the bar, that's the volume. So any repeated shape is just the area of the shape times how long it's repeated. Okay, I love you guys. Did you need to know any of that for this number? That's a cylinder, correct? A cylinder is pi r squared times h. If I cut a cone out of it, I need you guys, can you see in your mind a cylinder? If I start to whittle down the sides and I cut a cone out of it, I end up cutting 2/3 of the wood away, or whatever that material was. So I'm left with 1/3 of what was there. So the volume of a cone, is 1/3 the volume of the cylinder it was cut out of. Neat. If I gave you this problem on a test, I would give you the formula. Yes, I'm not going to suddenly make you, hey, remember all of geometry? No, I'll give you the damn formula. It's not a big deal. What is different about this formula compared to any other ones we've been working with so far?
Has a fraction.
The 4/3 had a fraction, so that's not different.
There's a whole other variable.
Good. There's more variables than normal. That sucks. Because what is r squared times h? That would be product rule, and then I would have dh dt running around. I'd have dr dt running around. Do you want any of that to be true? And you're sitting here going, I don't want any of this to be true, Jeff. Is that an option? No, do it. So, what is part? I forget. I forgot how much I broke this problem down. What's part B say? Part B is on the back. Turn your page.
Finding an expression for the volume of water in the tank.
Yes. So we've got that, yes? Because we chose R and H for our variables. There's an expression for the volume of water in the tank. At least I don't say wash my car. How we all doing so far? So I've got a relationship between my variables, but I think we all agree the number of variables is too damn high. We want to cut down on that. Look at part C. How in the shit would I get a relationship? I think you all agree with me that at a specific height, there will be a specific radius. So we know there's a relationship between height and radius. How in the shit would I find that relationship? Let me ask you this. Where's the radius start? In the center. Can you guys draw a line cutting down the center? Good. Draw a line cutting down the center. What shape did you just make? Holy shit. In fact, how many triangles are there? 2 right triangles, yes? So if I just take a moment and I copy down, I'm going to turn it this way. This is 20, yes? You don't have to do that, Jeff. Here's my R. This is 60, and here's my H. Does that look at all familiar to something we did before?
Similar triangle.
Yeah, similar triangles. Can you set up a proportion that would be true? So there's somewhere between 1 and 7 problems in your homework that involves similar triangles. And they're not going to be drawn for you. You need to be able to realize they're in there. And this is a really good example of that. Until you drop that down, you don't even realize necessarily that there's similar right triangles. Can somebody share with me what you've written for your proportion?
60 over 20.
60 over 20 equals?
H over R.
H over R. I love it. Big height to big radius equals small height to small radius. Kick ass! And of course, 60 divided by 20, last time I checked, is 3. Okay, now. Let me remind myself when I tell you this. Oh, okay, good. From the very beginning, that's right. Okay, beautiful. I love it. I'm being kind of nice to you in part D. Look at part E. It says, what rate is the radius of the water decreasing in the radius? Okay. If that is the question in the problem in the book, they wouldn't ask you this before we got here. But what is the only variable besides volume that would matter to this problem? What are the variables again? V, R, and H. So what's the only variable this problem cares about? R. So which variable do we want to get rid of? H. Do I have a relationship between H and R? So here's where students, I think, could turn around a little bit. What would I solve this for?
R.
Nope. I want to solve this for H. Because then if I replace H with that, I will only have R left. This is substitution method. Can you solve this for H? 3R. And if I bring back, so whenever you want to get rid of a variable, you solve the relationship for that variable, because then when you substitute, you've effectively gotten rid of it. This is an invasion of the body snatchers. In the middle of the night, they come in and take H and they replace it with 3R. Can you guys go ahead and do that? Simplify the volume if you replace H with that. Yeah, that's fine. Yeah. We can live with that. What do you think? Oh yeah. Yeah, this will be nice. Okay. So if I shove this in, I'll get 3R, and then these 3's cancel, and the R's go together, making it pi R cubed. That is a much better equation now, because volume is only a function of radius. That is going to happen every now and again. A decent number of these problems are going to happen randomly again. And I always forget that this is a part of this kind of problem. This is what they tell us, and this is what they ask us. If I can use, let me put it up here. Use what they tell me in what they ask me, I can get an equation that I can work with directly. Can you do part E now? Go for it. Try to do part E. If you have no clue, call me over. Yeah.
I have no clue.
Do you understand some of, like, all right, this is the equation that would be given to us. And of course, that's what we chose the water to be at, was H and R, I guess.
Mm-hmm.
Okay. This is just because of the similar triangles, yes? And now that we know H is this, I could just plug it in here, and then we get there. Okay. Now I want to find what rate is the radius decreasing when the radius is this.
Okay.
And from earlier, I know how quickly the volume is changing, yes? So obviously, what do I want to do with this then? So I can use all that information. We have information on how much the volume is changing per time, and I have information, and I want to know how quickly the radius is changing. So what do you want to do with this?
You just plug in 16 to that formula,
Of course not. Because that would just give me the volume that's when it's 16 feet.
Yeah.
That's not what the question was.
Oh, it's
What was the question?
It was right there. At what rate is the radius decreasing? So listen, what symbols would represent that? R is radius.
Yeah,
What
R is
represents the rate of change of R with respect to time? What symbols?
Second.
So like area, the rate of change of area would be dA dt.
Oh, dA dt.
So what's the radius change?
dr dt.
dr dt.
Okay.
So obviously, in order to have dr dt show up, what do you have to do to this equation? Yeah. So I take a derivative, and then I can shove in everything I know, and the other thing I know is what dv dt is.
Thank you.
Anytime. It's like my job or something. I mean, effectively, whenever you see them say, at what rate is this changing, then you know you're going to take a derivative. So this derivative is not too crazy, right? Now, from the other side of the paper, we know what dV dt is. It was 48 pi cubic feet per second. Again, very precise drainage. And what's the question want from me? What symbols does the question want me?
radius.
So what symbols is that?
dr dt.
dr dt. So I see dv dt, I see dr dt, I see r, but thankfully they told me what r was. So the radius of the tank at the top is 20. So if it was full to begin with, and then some kid puts a hole in the bottom and it starts to drain, well, okay, a few minutes later it's going to be down to 16 feet. So now I'm curious, at that point, how is the radius changing over time at that point? And so once I get a function that has only one independent variable in it, I take the derivative and I can just start to throw in what I know. So I know this, I know this, and now I can solve for this. So let's see, like 3 times 16 is 48, that goes goes over there, and it goes over there. So I get 1/16, I get 0.06 something, I think. Yeah, should be 0.06 something. Has anyone gotten the answer yet? So you divide this by 3 pi 16 squared. Throw that in the old calculator, and I think it should come out to be 0.06. Yes? Is it 0683 or is it 0625? 2. I'm sorry, I worked hard. What's the units on that? What's the units on that?
Centimeters. No, feet cubed.
No. Radius is in feet, not cubic feet.
Over.
Time,
Which is second.
and this problem I think was seconds, yes.
That's on Thursday's quiz, right?
By the way, just to make sure you guys understand. Yes. This is volume, correct? This is cubic feet. What was this? What was 16? Radius, feet, yes? Squared. Cubic feet divided by square feet is feet. That's another reason why that's feet. Do you actually have to look at it like that? No, you can just look. Radius is in feet. Time is in seconds. Rate of change is feet per second. That's why this notation is so much better than the prime notation, because I can see the units. Okay, maybe. It's your new favorite thing, yes? Sorry. Some guys are like, that ain't even funny, man. Shut up. Okay. All right. We just got to get in there and try these. Right? Okay. So, one more thing in chapter 3. So here's the. Let me make sure you understand how this class works. Wherever you are in the homework, if I were you, wherever you are in the homework, maybe do some of that, and then take a minute and do the first several problems from 3-9, so that tomorrow you have specific questions to ask, because we're all crazy. We're taking a 6-week calc class. Thursday we got a quiz on this. Yay! So you could ask questions tomorrow if you let yourself try some of them out. So wherever you are in the homework, just put it aside for a second. Try a few out from this. Yes? Now tomorrow's quiz is 3536, which hopefully I was hoping you come today with questions. So be ready for that tomorrow. So we'll see. Okay. So, how do I transition here? So related rates is a thing. Now, we all know it's a thing. It's there. There's a decent number of parts to a problem. If you just do each part one thing at a time, you'll be fine. You got to get in and get some practice. There's a problem involving the shadow of somebody that's very interesting that trips people up very often, understandably. What was the other one I was thinking about? There was another problem that gets really trippy. I can't remember. Most of the ones I assigned, I think, are pretty straightforward, but we'll see if you agree with me. What we're about to get into, the last section in chapter 3, is finally coming back to tangent line and going, you found the tangent line of a lot of stuff. Yes? What can we use it for? Is there a purpose for it besides just finding it and graphing it and going, ooh, does it have a purpose? And it does. And I think I pretty much showed you this before in a certain way. So let's do this. I'm gonna show you how to do the problems in this section using what we already know. And then I'm gonna show you the way they present it. And they try to make it sound like something brand new. So I will show you the connection between what we're about to do and the way that they show you. Okay. So if I give you this equation here, and I say find the equation By the way, that's a quick way to say equation of the tangent line to f of x at x equal to, what sounds good, Jeff? 2, sure. All right, so this is old news. We found equation tangent. If you've been doing the homework, you've been finding so many damn tangent lines, you're about to go crazy. How do I do it?
Either three.
That's crazy. 2 things I need. I need the slope, and I need a point. So to find the slope, we're in calculus. To find the slope, we find the derivative first, which is, and then if I plug in a what?
The point
2, I'll get the slope I need for this problem, yes? What do I get when I plug a 2 in? 10. Okay. So I know the slope now. How do I get the point?
Use the y minus.
No. I can't use that yet until I get a point. Yeah, I use the function. The function's what's this guy's purpose?
To get a point.
To get a point. He makes points. And what does he make? Slopes. Good. So if I need a slope, I go to him. If I need a point, I go to him. So when I plug a 2 into this, what do I get? Yeah. So I get 8 minus 4, I get 4. So then my point is 2, 4, and my slope is 10, and that's a relatively easy thing, right? So if I get the tangent line, what do we get? I keep doing this because today is going to be where you see one reason why I keep going back to this form. Y minus the y piece equals m times x minus the x piece. Okay, is everybody with me? By the way, you want to see how I do this shit? I look at this and I go, oh, when I plug a 10, when I plug a 2 in, that's 20 so far, but it's supposed to be 4. Oh, I better subtract 16. All right, or you do all this shit if you want that. All right, now, that we've done before. That's old news. We found tangent lines like crazy. And if I graph it, it does it like we know it should, and ooh, we stand there and we go, ooh. Here's the power of a tangent line. Do you all agree with me that this formula, this function, is much nicer than that function? Do you all agree with me, though, that this function is relatively not that bad?
Yeah.
But I could make this function as disgusting as I want to, and what will this function always be? It will be a line. So however bad this function gets, this process gives me a line. Now, what is that line's job? What is his job? His job is to approximate outputs for the original function near this point. Because when we graph it, what happens? When I'm really close to this point, it lines up really well. It hugs the function pretty well. The minute I get further away, that distance between the two gets really big. I've shown you pictures of this before, yes? So the tangent line, the minute I get any distance away, the difference between the tangent line and the function gets pretty big, depending on what the function is. But really close, it's really, really, really there. And in fact, I think one day I started all zoomed in, and then I zoomed out and showed you.
Yeah.
They were actually not the same thing, but when I get really close, they look almost the same. So here's the thing. If I wanted to approximate f of, what you got, Jeff? 2.2. So to find what f of 2.2 is, I would plug it in here. Do you want to do 2.2 cubed in your head?
No.
Okay. But the problem says approximate. So this guy gives me approximate answers. So if I plug a 2.2 into this guy, this is y evaluated at 2.2. Can you do this in your head? Yes, you can. What's 10 times 2.2? Minus 16? 6. Stay with me. That's an approximate number, and depending on how important it is that I'm exactly right, that number's fine in a lot of applications. Can somebody please, and I know somebody's doing it already, can you plug 2.2 into this and tell me what you get? Don't say anything yet. Give everybody a little bit of a chance, including me. Minus 4.4 is 3.68. No, 3 point. I lost track of it. Somewhere around there. It can't be that, Jeff. No, I must be very wrong. 2.2 cubed. I must have got that wrong. Oh, I did get that wrong. I should stop trying to do this in my head. It's too much. It should be close to 6. 6.24, blah, blah, blah?
Yeah, 6.24.
Cool. All right, so the actual value is 6.24? Is that what you guys said?
6.24A if you want to round.
No, 6.24, blah, blah. All right. Not too far off. 6 is a good approximation for 6.24. If I try to do this at 2.7, what do you think would happen?
So a little bit farther on.
My approximation would be worse. If I try to do it at 2.03,
Might be close.
It would be close.
it's going to be really close. Let's try it. So just remind everybody, including me, the function was x cubed minus 2x. The derivative, the tangent line was 10x minus 16. So if I try to plug in 2.03, that'll be 4.3, and f of 2.03. I think that's what that is.
Yeah.
Cubed minus
4.305.
All right. How close are these?
Very close.
Stupid close. They're only 0.005 away. This is a computational analog to our visual of the function getting further and further away from its tangent line over time. Computationally, the outputs are getting further and further away. Yes? I don't know if you guys are really with me. Okay. So what is one use of tangent lines? To approximate any given function. So here's what it looks like in this section. What did we do? We created the function, the tangent line, by doing this, yes? So let me do this. Let's say x1, let's call it a. So that is going to be the point around which I want to build this. I want to build a tangent line around an input of a. What is this then?
Slope.
Be very specific.
The slope.
How would you find it specifically? So I'm sorry, let me be careful. Given a function f of x, I want to create the tangent line. So how would you find the slope very specifically? Find the derivative and then plug an a in, yes? Is everybody cool?
Yeah.
That's exactly what we did a minute ago, yes? Okay, I love it. How would I figure out y1?
By plugging it into the original.
Yeah, take the original function and plug the a into it, yes. So what does this look like then fully? I'm going to do one thing before I start plugging stuff in. I'm going to add the y1 over. Okay, so I just added the y1 over, yes? So y1 is f of a, m is f prime of a, and x1 is a. And if I remember correctly, I think the book calls this L for linear approximation. Yes. L for linear approximation. Now, if you look at this formula, if I just taught you this formula, you would think everything was new. This section is brand new, and I really hate that. That's just the dumb tangent line formula written more formally. But we made the tangent line. This is what we did. So, of course, that's just the tangent line. That's all it is. So when they say use a linear approximation to estimate this function evaluated at 7. Well, do everything we did before I even wrote this shit down. Now, you could look at it this way if you like looking at it this way. It's not a damn thing wrong with this. Yes? So let's do one more example. Here's a really neat function. Let's do a square root function. And let's try to do it this way, just for fun. And I want to do it around x equal 4. Sure. What's my first thing I can do? There's a few answers I'll accept. What's the first thing I can do? Take a derivative, plug the 4 in. I love it. Those are the two main first things I could do. I could plug a 4 in to get my point. And over here I can take a derivative. Now if I rewrite this, it's x to the 1/2. So what's the derivative?
1/2 x.
Good. Which if I wanted to, I can write as 1 over 2 square root of x. Right, the square root of x goes down, the 2's already down there. Yes?
When you call it more correct, there's something that you want us to do where we write it as 1/2 over 2 x.
Do it again, sorry.
1 over 2 x.
Oh, either one of those is fine to write it as. Yeah, you're right. Either one of those. It's just, we're about to plug numbers in, and we're so used to radical notation that when I'm about to plug stuff in, I might as well make it a radical again. Because I know what the square root of 4 is. But if I said, what's 4 to the negative 1/2 power, you're going to go, wait a minute, right? Because we were brought up with fractional powers. Because the very next thing I need to do is plug a 4 in, yes? So it'd be 1 over 2 square root of 4, which is 1/4. Okay. So if I plug into this then, f of a is 2. So the linear approximation is 2 plus 1/4 x minus 4. Which I could simplify quite a bit. So what if I wanted to approximate the square root of 4.4? I want to approximate what that is. How would I do that?
Plug it into
Yeah. If I want an exact answer, I got him, I would plug a 4.4 in. I want an approximate answer, so I'm going to plug a 4.4 into him. That's his job, is to approximate what he would say. And what's 1/4 of 4.4? 1.1 plus 1, 2.1. Can somebody check to see what the square root of 4.4 actually is? Do it again.
2.097.
2.097. 2.1 is pretty freaking close. And again, a square root function is really well behaved. So the tangent line actually works for a good little while. If I have a function that goes crazy, my tangent line's only going to work for a little bit. Okay, I like it. Good job. There are some new elements to this section, but the main part of this section is not new. And I hate that the book makes it feel like, oh, look at this new shit. No, it's just the first application of tangent lines. So let's talk about what's new. If I have any paper left, damn it. Even though I don't, we're going to talk about it. I forgot to go get some more paper. Rah, rah, rah. All right. There's stuff on the back of that one. There's stuff on the back of that one. That one's down there now. All right. Somewhere I have paper left. Do I? I do. Okay. That was exciting. All right. Here's the new parts to this. So if I have a function, and let's say I get, let's look at the derivative. All right, I'm going to do a little something. I'm going to zoom in on this in a second. But if I want to kind of approximate what the derivative is saying, this would be dx, and this would be dy. And then that would be sort of like leading to the tangent line. So let me zoom in. Well, actually, can I just use a picture out of the book? Maybe that would be better. Yeah, perfect. All right, let's look at this. Instead of me trying to draw it, it's already made for you with a computer. So this is zoomed in. So my function is the blue line. Is that cool? The function is the blue line. The red line is the tangent line. Are you guys with me?
Yeah.
So this is dx, which is also delta x. So let me slow down a bit. Do you guys remember this was the big change in x, and this is the infinitesimal change in x? I don't like the book says this equals that, because that's not really true. But for the purposes of estimating, that's fine. dy is what gets me to the tangent line. Because what builds the tangent line? The slope builds the tangent line. Are you guys with me? Because the very first thing we do to get tangent line is to get derivative. That's how I'm going to build my tangent line. So dy would be the estimate change in y. Delta y is the actual change in y. So here I'm on the blue line. Everybody agree?
Yeah.
Okay, and I'm not going to transfer it to the red line. If my input changes by this much, my output actually changes by that much. But my predicted change in my output is that much. And that's basically what we've been talking about, that difference in height. So the further out I go from the point that I built things around, the worse that difference gets. I love it. So here's the use, how we use this stuff. So this is kind of silly. Let me zoom in on this a bit. We just look at this directly. You didn't have to do that, Jeff. So if I go from here to here, this, let's call this x, and we'll call this x plus delta x. So this is delta x. Oh boy, oh shit. What is this then?
That point.
Let's say this is f of x, yes? So that would be f evaluated at x, yes? That's f of x. And what would this be here?
Delta y.
This would be, careful. No, this is delta y, I agree. This would be f of
X plus
delta x. I love it, okay. Do you see how delta x is kind of like acting like h from,
epsilon delta.
well, from limit definition of derivative? Okay. Has it been turned like that for a while? I'm sorry. Okay. So, all right, this is kind of silly, but what would delta y equal then? Delta y would equal f of x plus delta x minus f of x. Oh shit, you can't see it. You guys at all with me? That is literally how to figure out how big that is to take this output minus this output. See how different they are. Ooh. But what would dy be? Help me out. If y is f of x, what is dy dx? F prime of x. I love it. So what is dy? How do you solve this for dy?
Multiply by d of x.
Yeah. So that is an estimate for this. Let me say this again. This estimates this. This is the actual change that I saw. This is the estimate at a point. Okay. And this is exactly related to, believe it or not, kind of like, shoot. We've talked about this several times this semester. If I have a slope at a point and I move a little bit, I can make a guess, but why is it going to be off? Because the minute I move, the slope has changed. And that's why this is a slope evaluated at a point. It's only going to be an estimate for this, because this guy just takes the difference in the actual outputs. He kind of cheats. He's like, I know the answers. And this is me going, I don't know, I'm going to estimate. Okay. So just to show you here, I'll just show you this example directly. Compare the values of delta y and dy. So if I'm given this function, delta y would literally be just plug a 2.505 in, plug a 2 in, take the difference, yes? It's f evaluated at one end minus f evaluated at the beginning. How would I figure out dy?
F prime.
Yeah, first I take the derivative of f, yes? And then I would plug, now here's where it gets tricky. Do you see where they take the derivative of, shoot, put your glasses on. There we go. Where are they doing which one? Here we go. There's the dy, take the derivative, but then they plug a 2 in because the derivative estimates based on where you start. So do you see the actual change was this, and the estimated change was that? Okay. I love it. Now, this type, okay. A lot of you guys, have I said this already, that calculus is like where math starts? Did I tell you that? This is an idea that builds and eventually gets into things like tolerance in machining parts and so forth. It's the differentials, how far are you allowed to be off by. So much of what we're talking about is the beginning ideas to these larger things. If you go into engineering, you're going to look at this more detailed and in more specific ways. If you don't go down to engineering, you might look at this in a very different way, but it's the same idea underneath. So my point is, a lot of the time we don't see the full use of this because, again, we don't have enough information yet. You'll see more uses for this depending on where you go next. But for right now, it's just a matter of getting used to using these two things, these two ways of looking at things, this one versus this one. And I think that's, yeah, good, okay. So the main thrust of 310 was, what can I use tangent lines for? And another name for tangent line is linear approximation. Because that's literally what it does. It's a straight line approximation for some given curve. Okay. So the last thing I want to do today, you're doing so good. Oh man. I have one more handout. We're going to do a little bit of this and I'm going to let us out on the roll as always. But I do want to get just a little bit into this. And compared to everything else we've done today, I'll just let you look at this and see what you think of it. We're not quite getting into chapter 4 yet.
Yeah. Absolute maximum. That's a new thing right there. What do you explain? Oof.
Give me one. So can you guys just real quick, these are very surface level. They don't require much thought, but I like to do this worksheet. I made this worksheet a couple years ago. I think it's a really good idea. We're looking at what we're about to do a little backwards. You have a fully fleshed out functions graph. So you can see the answer to all these things. So I didn't even define what the word local means, but can you tease out what it might mean? So can you go ahead and try to answer the first 4 questions up there?
Would you put E for local routes?
let's go with that. Well, then that's the thing is that's the wrong axis, right?
Let's look at this kind of backwards for a second. What's definitely the absolute max location?
E.
Okay, that's an absolute max. Yes? Local maxes and mins require neighborhoods to be. So like a local max would be the winner of a regional contest. Yes? In order to win there, you have to have kind of like a region around you. So the endpoints can never be local maxes or mins. They could be absolute, but they can't be local. The local maxes and mins, therefore, who's got an idea for the only local max there is? There's only one local max. C. Locally, that's the highest point, yes? Why is it not an absolute max? Because at some point, something gets higher. So did it win the local competition in its little neighborhood?
Yeah.
Yep. And that word neighborhood, by the way, is the technical math name. This is a neighborhood of C. How many local mins are there?
2.
2. What are they? Where do they occur?
B and D.
B and D. What happens to be true about D?
It's lower than.
So it's also the what?
Absolute.
Absolute min. So endpoints could only be absolute if they are anything. Was this endpoint anything?
No.
Poor him. Yes. He was nothing. Absolutely nothing. Local maxes and mins have to occur inside the interval. Yes? They can't be at the endpoints. They have to have an area around them to be the local winners. Okay. Maybe. Are you guys kind of getting the feel for this?
Yeah.
Can anyone identify something that was true where the local maxes and mins were? Is there a certain aspect of the graph, maybe calculus related aspect of the graph? What about the slope at the mins specifically?
0.
Yes. Now, could I have made like this kind of a shape? This would have been a local what?
Max.
But the slope here is also
0.
Okay, good. So either, does this make sense? Could you draw a continuous function as a maximum where the slope is not 0? The only other way to do it is this way. What's the slope there? Beautiful, because it's a kink. It's an undefined slope. If you can come up with a way to draw a local max that's neither 0 slope nor undefined, teach me. So here's the idea. We kind of came up across this idea backwards. Normally when you teach calculus, you say, let's find the critical numbers, and then the critical numbers, blah, 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 blah. And you say, take the derivative, set it equal to 0. But I'd like to start with this. Because if you think about it, there's no way in hell to make a maximum of a continuous function without either making the slope 0 there or undefined there. There's no way to do it. Therefore, if I'm just given a function and not the graph, how do I find its maxes and mins? What do you think I do, based on what we just said?
Find where the slope is 0.
Find where the slope is 0 or
Or the
undefined. Now, just to put a kink in this, and then I think I'll let you guys out of here because looking at some of your faces, I'm pushing my luck. Is this a location where the slope is 0 right there? Is that a slope 0?
No. Well,
It would be if I kept going, yes?
yeah.
But what if I do this?
No.
That is still 0 slope right there, yes? Me being more precise. That is still 0 slope right there. You agree?
Yeah.
Was that a max or a min?
Yeah.
Trick question.
Yeah.
Trick question. Was that a max or a min? I'm telling you it's a trick question. That is neither a max or a min, yes? Locally, is it the highest point? No, because something over here gets higher. Is it the lowest point? No, because something over here gets lower. So, if you take a function, its derivative, set it equal to 0 or undefined, those are the possible maxes and mins.
How do you make sure?
And then the next thing we talk about is, how do we determine which ones are the maxes and mins? That would be the next step. Okay, all right. I almost got to where I wanted to. That's plenty. So don't forget tomorrow what's going on. A beautiful quiz. So 3, 5, 3, 6, and then the next day, another quiz on 3, 9. Everybody's favorite section for rates. Okay, I'll see you tomorrow. Oh.
Wow.